Hello. This lesson covers the first part of Chapter 7 on asymptotics. In this part, we discuss the big O and big omega notation. Big O and big omega notation. I revised the material, so the material is not quite identical to the textbook. I hope to update the textbook in the near future. Let's start. We're interested in functions that describe the number of gates in a circuit, the delay of a circuit, in other words, the length of a longest path in a directed acyclic graph, the running time of an algorithm, or perhaps the number of bits in a data structure. In all these cases, it's natural to assume that the function we're looking at satisfies for every n, f of n is greater or equal to 1. So this is the formulation of the assumption that we will use throughout this chapter. Our goal is to compare the rate of growth of functions asymptotically. By this we mean, how fast does the function grow as n tends to infinity? In this chapter we ignore constants, not because constants are not important, they are important in practice, but simply because we want to focus on high-order terms. So for example, in this graph, the x-axis denotes the argument n, the y-axis denotes the value of the function, and we have here two functions, the green function and the red function. We see that for the low values of n, these are the low values up to here, the red graph is below the green graph. However, for the high values of n, we see that the red graph is above the green graph. And therefore, we would say that asymptotically, the red graph is above the green graph. Let's formalize this definition. So we have two functions, f and g. As our assumption says, the range of these functions is greater than or equal to 1, and the real numbers that are greater than or equal to 1. And we want to define what it means that f of n is big O of g of n. And the definition says there exist constants, c, which is positive, and n, which is a natural number, such that for every lowercase n greater than uppercase n, f of n is less than or equal to c times g of n. The definition f of n is big omega of g of n is very similar, same constant as before, same distinction between high values of the argument and low values of the argument. The only difference is that here we have less than or equal to, and here we have greater than or equal to. So f of n is big O of g of n if f of n is less than or equal to c times g of n for some positive constant and sufficiently large values of n, and f of n is big omega of g of n if f of n is greater than or equal to c times g of n for some positive constant c for sufficiently large values of n. We say that f of n is big theta of g of n if f of n is both big O of g of n and big omega of g of n. Now, when you read this definition, you may wonder, what does this equality sign actually signify? Okay, so let's talk about this a little bit. When we write big O of g, we actually mean a set of functions. So big O of g is the set of all functions h, for which there exists a constant c, which is positive, a natural number n, such that for every lowercase n greater than uppercase n, h of n is bounded by c times g of n. And when we write f equals big O of g of n, we actually mean f belongs to this class of functions, to this set of functions which we just defined above here. So it would have been better to write f is a member of big O of g. But instead we write f equals big O of g, and we actually read it f is big O of g rather than equals. This is a very strange notation and very confusing at first. Why do we use it? Well, we use it because we plan to abuse notation. And this is one of the hardest parts, getting to understand how notation is abused and not being confused by it. Eventually, we will want to write expressions like the following. We'll have some function and another function, perhaps take their product, and we'll write this is big O of a product of two functions. This is because what is written here in yellow is big O of n squared, and what is written here in orange is big O of log of n squared. And then we might want to further develop this expression and simplify the log of n squared to log n, because, as we will show later, big O of log of n squared is log of n. So, when we write such a sequence of equalities, we actually mean that the first function, let's call it f, and let's call this the second function g. We actually mean f is a member of big O of g. And let's call this function h. We actually mean g is a member of big O of h. Okay? But we abuse notation and we just write here equalities. But these equalities are not the standard type of equalities, okay? You cannot write, for example, big O of g equals f. This does not make sense, okay? Does not make sense. Okay, so don't do that. Okay, good. Let's continue. Given this definition of big O, big omega, big theta, one way to understand what this definition says is that if f is big O of g, then asymptotically speaking, f of n does not grow faster than g of n. If f is big omega of g, then asymptotically speaking, fn grows at least as fast as g of n. And if f is big theta of g, then asymptotically, f grows as fast as g. I want to make an important remark that if you are asked to prove that f is big O of g, it is not necessary to find the smallest constant. For example, suppose you want to prove that n plus square root of n is big O of n to the power of 1.1. It would suffice to prove that for n, which is, say, greater than 2 to the 100, n plus square root of n is less than 1,000,000 times n to the power of 1.1. These constants, 2 to the 100 and 1,000,000, are not really important. Any other constants you can prove the statement for are just as good. Let's see an example. We want to prove that n is big O of n squared. So we want to prove that there exists a constant, which is positive, and there exists a natural number n, such that for every n greater than n is less than or equal to the constant times n squared. Well, this is trivial. Just pick c to be equal to 1 and n to be equal to 5. And you can check that indeed this holds. I have no interest in optimizing the constants here. I could make this 100 and I could make this 556 as well. This would be no problem. The second example, I claim that log n is big O of n. Let's see why. I need to prove that there exists a constant, which is positive, and that there exists a natural number, such that for every n greater than uppercase n, log of n is less than or equal to c times n. And indeed, I can do this very easily. I can pick c to be 100 and n to be 55. Okay? And you can easily check that log of n is less than or equal to 100 times n for any, this is capital N, for any capital N, for any n which is greater than 55. Here I'm looking at the following case. 10 times n is big O of n. 10 squared n is big O of n. 10 to the power of 100 times n is big O of n. And this is trivial, because all I do is I take the constant to be this constant, and I immediately get that the constant times n is less than or equal to the constant times n for any n. On the other hand, if I multiply n by a very small value for small values of n, this is a very small value, but it tends to infinity, right? Log n tends to infinity as n tends to infinity. It tends to infinity very slowly, but it is unbounded. Therefore, n times this function, which tends to infinity, is not big O of n. Okay, because if I were to try to bound n times log of n by some constant times n, and I were to divide by n, then I would get that this function needs to be bounded by a constant, which it isn't. And therefore, it does not hold that n times log of n is big O of n. Now, suppose I tell you that f of n is big O of 1. What does this mean? Well, what is 1? 1 is a constant function that for every argument gets the value 1. So we claim that f of n is big O of the constant function 1 if and only if there exists a constant c such that f of n is bounded by c for every n. Now, if there exists such a constant, such that f of n is less than or equal to c for every n, then clearly f of n is big O of 1. This is by definition. Let's see the other direction. If f of n is big O of 1, that means that there exists a positive constant c prime in a number n such that for every lowercase n greater than n, f of n is less than or equal to c prime. That means that for every n, f of n is bounded by the maximum of c prime, f1, f2, f3, up to fn. For the big numbers, for the big arguments, c prime is an upper bound. For the small arguments, those that are less than or equal to n, I've written here the values of the function. So f of n is going to, for every n, is going to be bounded by the right-hand side. Okay. Let's see the following situation. I have two functions, f1 and f2. Both of them are big O of g. And now I take their sum, f1 plus f2. Then I claim that f1 plus f2 are big O of g. Let's see why. Because fi is big O of g, I know that there exists constants ci and ni such that for every n greater than ni, fi of n is less than or equal to ci times g of n. This is exactly the statement. Now let's take the sum of f1 and f2. Well, f1 of n is bounded by c1 times gn. f2 of n is bounded by c2 times g of n. And this bound holds provided that lowercase n is big enough. It has to be bigger than n1 and n2. So let's take n to be greater than or equal to n1 plus n2, in which case we know that this lowercase n is sufficiently big for this inequality to hold. And we found a constant, which is in fact c1 plus c2, for which f1 plus f2 is bounded by c1 plus c2 times g. As a consequence of this claim, let's look at the polynomial n squared plus n plus 1. N squared is big O of n squared. n is big O of n squared. We already saw that. It's easy to see that 1 is big O of n squared. So I take the summation of three functions, each of which is big O of n squared, and therefore their sum is also big O of n squared by this claim. Okay, so I already used the abbreviation Fi is big O of h, meaning that Fi of n is big O of h of n. Now suppose I have functions f1 of up to fk for a constant k, and each fi is big O of gi. Now I can take these functions f and these functions g, and I can build new functions from them. For example, one function I could build is the maximum of the fi's, or the maximum of the gi's. The first part of the claim states that if fi is big O of gi, then the maximum over all the i's of fi is big O of the maximum of the gi's. The second part of the claim says if I take the summation of these functions, it will be big O of the sum of the gi's. And if I take the product of these functions, it will be big O of the product of the gi's. Before I prove this claim, let's see two consequences. So 2 is big O of n, and n is big O of n. So I can take the product. 2 is big O of 1, and n is big O of n. So I can take the product 2 times n and bound it by big O of 1 times n, which is n. Okay? So I can prove that 2n is big O of n by using this claim. It's not a very sophisticated application of the claim, but it follows by the claim. Now let's look at what happens here. 50 times n squared is big O of n squared. 2n is big O of n. 1 is big O of 1. So the summation of these three functions is big O of n squared plus n plus 1. Now, what can I say about n squared plus n plus 1? Well, we already saw in the previous slide that n squared plus n plus 1 is big O of n squared. So therefore, if 50n squared plus 2n plus 1 is big O of n squared plus n plus 1, and n squared plus n plus 1 is big O of n squared, then I get that this left-hand side is big O of this right-hand side. I will formalize this transitivity, which I just applied, shortly. Okay, so now let's prove the claim. So suppose that fi is big O of gi. I want to prove that the new function, which is the maximum over all the fi's, is big O of the new function, which is the maximum over all the i's of gi. Okay, so since fi is big O of gi, I know that for every I there exists a constant, a positive constant, ci, a natural number, capital Ni, such that for every lowercase n greater than or equal to uppercase Ni, fi of n is less than or equal to ci times gi of n. Now let's define the constant c and the constant capital N to be the maximum over all the constants ci and the maximum over all the constants ni. What do we know as a result? For every n which is greater than or equal to this n, the maximum of fin is bounded by the maximum of cgin, because fin is less than or equal to f1n is less than or equal to c1 times g1n, and c1 is less than or equal to c. And so on and so forth. We do it for f2 with respect to g2, fk with respect to gk. Now we can take this c outside, and we have c times the new function, which is the maximum of gin. The maximum of gin we copy, the c is swallowed by the big O. This we already saw. Now we want to prove that the summation of the fi is big O of the summation of the gi's. We use the same notation as before for lowercase c and uppercase n, and we get that the sum of the fins is less than or equal to the sum of the ci times gin, because each fin is bounded by ci times gin if n is sufficiently large. Now, each of the ci's is bounded by c, so we can take it outside, and we get this summation function times a constant, which is big O of the summation function. Finally, we want to prove the same thing for the products. Now let's use the same notation and introduce a new notation, C tilde, which is the product of the constants. We know that for every n which is sufficiently large, the product of the fi's is bounded by the product of the ci times gin. Now, the product of the ci's, I can take it outside, it's C tilde, and I get here the product of the gi's. This is a constant, so what is written over here is big O of the product of the gi's. And that completes the proof. Now, what happens if fi is big omega of gi, not big O of gi? Then the sum of the fi's is big omega of the sum of the gi's. The product of the fi's is big omega of the product of the gi's. But now, instead of maximums, we will have minimums. And I leave the proof of this claim as an exercise. And the consequences of this claim are written over here. 2 times n is big omega of n, because 2 is big omega of 1, and n is big omega of n. So I have here omega of 1 times n, which is omega of n. And here I have a very small constant, 1 over a million, times n squared plus 2n plus 1. It is still big omega of n squared, even though the constant here is very small. And the proof of this statement is very similar to what I did before. Okay, let's see 2 applications of asymptotics. Let's start with the arithmetic series. If an is an arithmetic sequence with a0 greater than or equal to 0 and the difference d of the sequence is positive, then the sum of I goes from 0 to n of ai, is big theta of n times an. Let's prove this. Sn is the sum. We already proved that it equals a0 times n plus 1 plus d times n plus 1 over 2. We open the parentheses using some algebra, and we get that Sn equals a0 plus a linear term, a0 plus d over 2 times n, plus a quadratic term with d over 2 as the coefficient. This part is theta of 1, this part is theta of n, big theta. This part is big theta of n squared. Now we take the summation, we get big theta of 1 plus n squared, and this thing, by the claim, where we add functions, a constant number of functions, is big theta of n squared. Now what this means is, if you have an arithmetic sequence, the rate of the growth of the corresponding series, you simply take the largest elements in the sequence times the number of elements you've added. Okay? This is the rate of growth that you get. Now, what happens if you're looking at a geometric sequence with the first element being at least 1 and the quotient or the ratio of the geometric sequence being greater than 1? Then the corresponding geometric series, the summation of the first n elements, or n plus 1 elements, it doesn't matter, is big theta of the largest element of Bn. Okay, so if you take any sum of Qi's, I goes from 1 to n, this sum is big theta of Q to the power of n, the largest element. And the proof? We already saw that the summation of the geometric sequence satisfies this equality. And now we do some algebraic manipulation. The coefficient of q to the n is b0q over q minus 1. And we have here some number we're subtracting. This is b0 over q minus 1. Now, this is clearly big O of q to the n, because you can ignore the term you're subtracting, and this is a constant. B0 is a constant, q is a constant, q minus 1 is a constant. So you have your constant before the q to the n, so this is clearly less than or equal to this constant times q to the n, namely, it's big O of q to the n. But we want to prove big theta, so we also have to prove big omega. How do we prove big omega? So for large enough n, the value that you have over here, after you have subtracted from it this constant b0 over q minus 1, you're left with at least a half of the value, because this tends to infinity. So for a sufficiently large n, this difference is greater than or equal to 1/2 of the term which is written over here. So Sn is, for a sufficiently large enough n, Sn is greater than or equal to 1/2 times this constant b0q over q minus 1 times q to the power of n. Since this is a constant, we get that this is big omega of q to the n. Let's try to understand whether big O is an equivalence relation. So clearly, f is big O of f. I will show you that if f is big O of g, it does not imply that g is big O of f, so we do not have symmetry. But we do have transitivity, namely, if f is big O of g and g is big O of h, then f is big O of h. So f is big O of h. What about big omega? The same properties hold with respect to big omega. Reflexivity and transitivity hold, and symmetry does not hold. I'll leave that as an exercise. So now let's prove the claim. We want to prove that even if f is big O of g, it does not imply that g is big O of f. And to prove this claim, it suffices to show a counterexample. Indeed, think of f of n, which is the constant function 1, and g of n as the identity function n. So 1 is big O of n, but n is not big O of 1. Now let's prove transitivity. F is big O of g, g is big O of h, implies f is big O of h. So if f is big O of g, then there exists a positive constant c1 and a natural number n1, such that for every n greater than n1, f of n is bounded by c1 times gn. And if g is big O of h, we have these constants c2, n2, such that for every n greater than n2, g of n is less than or equal to c2 times h of n. Okay, so now we take n, which is sufficiently large, is greater than n1 and n2, let's say n1 plus n2. And then for every n which is greater than n1 and n2, we have f of n is bounded by c1 times gn, and gn is bounded by c2 times hn. So now we have a new constant, c1 times c2, such that f of n is bounded by c times h of n for sufficiently large values of n, and that completes the proof. Another way to define big omega using big O is as follows. F of n is big O of g of n if and only if g of n is big omega of f of n. Okay, so let's prove it. Let's prove that if f is big O of g, then g is big omega of f. So if f is big omega of g, that means that there exists a positive constant c, a natural number n, such that for each lowercase n greater than uppercase n, f of n is bounded by c times g of n. Okay, now we can divide by c. We get that g of n is greater than or equal to 1 over c times f. Recall that c is positive. You can divide by c. Therefore, g is big omega of f, simply by dividing by c. I'll leave the other direction as an exercise. And this completes this lesson. Thank you.